was supposed to be an overview. What happened in terms of overview of a large body of subject is being put together. Naturally, there is a possibility of non-following or non-interest. Some of the people may likely to come. That's what from some of the feedback, that's what reflects. So actually it is a step-by-step process, like in a classroom teaching, a small portion in about 45 to 50 minutes. Then about 15 minutes question answer. All those things we could not, or it's very difficult in an overview lecture like this, because too many things are compressed, too many keywords are told, people will not be able to follow all of them. So that was a difficulty. So now, from today onwards, this is like a classroom. It will be very slow, and about 50 minutes of lecturing will be there. After that, we will give 15 minutes interactive session with the question answer. Okay, he will start. Some of this was discussed in the last class. So here, forgetting all that, there will be some repetition, but fairly repetition is good in this kind of online classes. You see, there is an aircraft here. There is an axis marked X, Y, and Z. Some names are given to that. Leave that. This is X, Y, Z of the aircraft body frame. It is called B frame of the aircraft. And that is an orthogonal frame, which usually we take so for a lot of advantages. And you have a frame, green color, sitting here. There is a local north and local east and local up. And we call this frame as east, north, up frame, because any coordinate frame that we will be using is a right-handed coordinate system. When you say right-handed coordinate system, if east is X and north is Y and up is Z, then X cross Y has to become Z, and Y cross Z should become X, like that in a cyclic manner. Such a coordinate system is called a right-handed coordinate system. Now, the coordinate frame shown here, called N frame, N stands for navigation frame. Some arbitrary, it could be different frames can be called N frame, but I'm calling this frame as N frame, navigation frame, in this particular example, which is three axes are east, north, up. And this is only applicable at this particular point. If you go here, the north direction will be like this, and the east direction will be like this, up direction will be some other direction. So this is a frame which changes depending upon your current location. So that is why it is called local geography frame. It depends upon the local geography of the user. So this N frame is told. And then you have a user vehicle here. And user vehicle is a vehicle which has got three axes marked here. It's called usually body frame, user body frame. Hereafter we will call body frame. Whenever say body frame, it is automatically we should understand that user body frame. When we say N frame, we should understand that immediately the navigation parameters are expressed in this navigation frame. So naturally we have two frames here. There is a navigation frame sitting here and a vehicle frame, user body frame is sitting here. What happens, suppose this particular aircraft is rotating or translating, the angular relationship between the N frame and the body frame of the aircraft keep changing. So there are two frames, say body frame and the navigation frame. Their angular relationship will be keep changing when the aircraft start moving. Now, this is one scenario. And usually, what we do is, the sensors, navigation sensors, they are inertial sensors. In the case of inertial navigation, they are accelerometers and gyroscopes, and they are fixed to this user vehicle along the x-axis of the vehicle, along the y-axis of the vehicle, along the z-axis of the vehicle, both acceleration as well as gyroscope axis. And actually, when this vehicle moves, these sensors measure the acceleration and angular rates in this body coordinate system because they are tied, they are fixed to this frame, to the vehicle. Now, we need to convert all those measurements taken, which we are getting in this body frame, along these axes, to a navigation frame which we use depending upon the application. In this example, this is the navigation frame, this is the body frame. Those measurements done here are to be transformed to this frame. So naturally what comes is a coordinate transformation from this body frame to the navigation frame. That is why the last lecture also we started with coordinate transformation. But this kind of example I couldn't put. Now this is one example. I go to the right side, you take a launch vehicle sitting on the launch pad. Of course, the launch vehicle convention that we follow is like this, X, Y, Z. It is again a right-handed system. X cross Y will be Z, and Y cross Z will be X, and so on cyclically. And this is the body frame in the case of a launch vehicle. It's a typical launch vehicle. This is not an international standard. This is, we can say, Indian standard. Okay. It doesn't matter. And you want to take a frame, navigation frame, which here I call I frame because an inertial frame. The last class we talked about what is an inertial frame. I repeat, because this has to be considered as a classroom. So I will repeat. Many things I will repeat. Repetition is good. Inertial frame is one frame which is non-rotating and non-accelerating. So, but Earth is rotating, and why I have shown this axis with the Earth and the Earth is rotating, whether this axis will be rotating with the Earth, that is a natural question. The last lecture it was explained, but I will repeat. What this I frame here, which is the navigation frame, to make it inertial, what I will do, at the start of the navigation, say at time t equal to t0, this x-axis going through this Greenwich meridian, through the equatorial plane, and the z-axis through the rotation axis of the Earth, and the y makes a right-handed triad. That means z x cross z, not x cross z, z cross x has to be y. So we have three axes, and at the start of the navigation at t equal to capital T0, these three axes I will freeze in space and time and allow the Earth to rotate, but I will not allow this x, y, z axis to rotate with the Earth. I will not allow. So little bit of imagination you have to have. To start with, I will define my x-axis, y-axis, z-axis like this. And then when I am starting the navigation, I'll say that let those axes remain in space and time like that. Don't allow them to move or rotate or accelerate, and allow the earth to rotate. No problem. So this x, y, z, in that manner, we have got an inertial frame. And this is a navigation frame used, inertial navigation frame used for navigating launch vehicle navigation. And so this is a nav frame. And here you have the body frame, which is a launch vehicle. Along the body of the launch vehicle, the sensors are mounted on the launch vehicle along the z-axis, x-axis, y-axis, accelerometers and gyroscopes, and they measure those accelerations and angular rates about this axis as the vehicle rotates, translates. The vehicle will be doing all sort of motion, and which will create acceleration, angular rate, and so on. So those will be measured by the sensors in this frame. So I again need to convert those measurements which are in this body frame now to my navigation frame, the inertial frame which I have defined. Again, you see there is a coordinate transformation is coming from this body frame to this inertial frame, which is my navigation frame. So again, the coordinate transformation of parameters, vectors from one frame to the other is essential. And once I do the conversion, I can do all integration and further processing. So therefore, what I want to say in this slide, the main point is, what is the significance of coordinate transformation? Coordinate transformation is one of the major elements in navigation. So today's class will focus on a small part of the coordinate transformation, not entire thing. So we'll go. This slide was put in the last class also, but maybe because the speed at which we have gone, I was not satisfied, so I am repeating. So I have a vector in space called capital V. I have two frames. Now you must be clear why I am taking two frames, because the previous example I told there is a body frame, user body frame, and there is a navigation frame, which in this case I am calling an inertial navigation frame. So I frame. Now this vector, if I represent this in this frame, I have to take the projection of this vector along x b axis, and then this will be that component. The same vector I have to take its projection along yb axis, and that is this particular component. The same vector its component along zb axis, and that is this component. So these three together, components together, represents this particular vector v in this body frame. I hope it is clear. Now let us see that the same vector, suppose I represent in this frame, how it will be like. Now, if I have to represent the same vector, the vector does not know. Please note, underline and note this statement which I am making. This is my characteristic statement. The vector does not know which frame are you using, are we using to represent it. That carries a lot of meaning in it. The way we look at is these frames are similar to the way we look at the vector. That's all. Now, if I want to represent this vector in this frame, along x-axis, I have to project this v along x-axis. That is cosine of this v into the cosine of the angle between this line and this line. I will get the component along xi axis. And similarly, the component of this along yi axis, v into the cosine of the angle between yi and v line. I get the component here. The first one will come here, second one will come here, and third one, the projection of this along is a axis will come here. Again, I am getting three components, you see. And this vector is the same. And if you look at this component and this component, they will be different. And this component and this component, they will be different. And this component and this component, they will be different. But if you take the magnitude of this, square of this, square of this, square of this, add them up and take square root, which will be equal to the magnitude of this. And here also you take square this, square this, square this, add up, take square root, you will get again the magnitude. The magnitude is not changed. That is because the transformation that we are making is a orthogonal transformation. I will be talking about orthogonal transformation a little bit later, which by a transformation, I should not increase or decrease the magnitude of the vector. That should not happen in our case particularly. So you see a given vector, when I represent in one particular frame, B frame, and the same vector I represent in I frame, their components are different. Now, between these two frames, the B frame to I frame, there is a relationship. So any vector given in this frame, I should be able to transform to this frame. That means I need a transformation matrix like this. What is this transformation matrix? Okay, let's at least one row we will just go through, other things will be automatic. Let's take, so this component gets multiplied by this component gets multiplied by this component gets multiplied by this to get the first component here. So let's see the physical meaning. How much of VXB component is there in VXI? That means VXB is along this particular direction. VXI is along in this direction. That means we need to take the cosine of the angle between VXB and VXI and multiply with this to get the component of this along the XI direction. That is the one. First element. Second element you see is getting multiplied with this one. BYB also can have a component along VXI. To get that, YB is along this YB direction. And here what we want is along YI direction. And therefore, you take the cosine of the angle between XI, finally, we want everything on XI. Sorry, YI is a mistake. So we want to get the component of BYB again on XI direction. So therefore, the cosine of the angle between YB axis and XI axis to be taken, and that multiplied with this particular Y component here will project this component onto the again on the XI axis. Like that, this also can contribute some portion to VXI component. There, the similar explanation what I told, the angle, cosine of the angle between ZB and XI, and that is this term, and that if you multiply with this, I will get the contribution or the projected component of this particular one onto VXI axis. So I got all the contribution of all the three along XI direction I add up them together, I get the first component here. Similarly, to get this, you have to, the other one is automatic, I hope, because you are all engineering students and it's matrix multiplication. I said it so slowly, so I think this is quite thing. Only thing is I want to talk about We have studied, in matrix, when we study the eigenvalue, eigenvector. We are not going to study in detail of that here, but to get some insight, this is a right place to give some insight, I felt, even though I have not seen in many books talking like this. Now, what is this is a 3 by 3 matrix, which DCM is being called direction cosine matrix, because each of this term are cosines of angles. All the 9 terms are cosines of angles, and that are talking about the direction relationship, and that forms a matrix 3 by 3, and therefore it is called direction cosine matrix. Okay. So normally what will be given when you are studying a matrix, it doesn't talk about is a direction cosine matrix or any other matrix. Simply they will ask, given this matrix, you find out the eigenvalues and eigenvectors. So here a specific concrete application area wherein we have got a coordinate transformation matrix represented like this. So naturally, this also has eigenvalues, eigenvectors. How many eigenvalues will be there? This is a 3 by 3 square matrix. There will be 3 eigenvalues, and this in this particular case, because it's an orthogonal matrix, which don't worry, that statement I will explain. One of them is real, and that is +1. The other 2 eigenvalues are complex, and that has got a different meaning. So right now we leave it. That +1, it signifies, I was earlier telling, whether this vector represented here, you take the magnitude, and here you take the magnitude, it is the same. That +1 eigenvalue says the magnitude of the vector is not changed. Suppose that eigenvalue had been +2, then this vector magnitude would have got amplified by 2 when it got represented in this way. But in our case, in navigation, we don't want the vector magnitude to be changed. So the eigenvalue of this particular matrix is, one of them is real, and that is +1. And there is an eigenvector corresponding to that eigenvalue. What is that vector here? Can we fix it somewhere here now? First of all, we are talking about 3 dimension. We have in this picture only 2 dimension. We are trying to visualize 3 dimension using 2 dimension. And in a 3 dimension, there are infinite vectors. And you will have, for this particular I frame, B frame orientation, there is a vector, there is one vector corresponding to the eigenvalue +1. And that particular vector, even if you represent in this frame or in this frame, the component values will be the same. And that vector is the eigenvector of this particular matrix, this particular coordinate frame, and that is the eigenvector of these 2 frames. This condition. So you see, the eigenvalues, eigenvectors is not only here, in many areas in engineering. This has got a lot of significance, even in signal processing, control, linear transformations, and so many places. That is, I'm just telling you to, if at all somebody is thinking interested, please give more focus on eigenvalues and eigenvectors. Try to get the physical meaning of that. So this is only opportunity I got, I mentioned. I hope you understood. Now, this is also the previous lecture I have put. It is repeating again here. Here, we have an X, Y, Z axis, right-handed coordinate axis, and the positive directional rotation about X-axis is shown like this arrow. And I'm giving a rotation by angle theta. And you know that YZ plane is normal to X. And this, when I do a rotation about X-axis, Y will go to Y dash by angle theta. and z will go to z dash by angle theta, and still y dash z dash is in the yz plane, and still all the four are normal to x-axis. And now I have two frames. One is x, y dash, z dash. That is the new frame I am calling. And the original frame x, y, z, and that I am calling old frame. So I have two frames here. And now suppose I have a vector represented in the new frame and written here. I written that little away, a vx, vy dash, vz dash. That is a vector written in the new frame, vx, vy dash, vz dash. And if you take the previous method of writing the coordinate transformation matrix for this, you will get this particular one. This we can very easily do it. So let's say that how much of Vx will contribute to Vx here, because when you rotate about x-axis, the axis remains the same. This doesn't undergo any change. Therefore, the entire Vx will come to this new x also. That is why here there is a 1, and the y dash and z dash are normal to x, and therefore they don't contribute anything. That's why these two zeros. Then let's see that the next, this vector, how much will it to the y-axis component in the old frame, how much it will contribute. You take Vx, the y dash is again, y dash to x if we take, is still normal. So it doesn't contribute, that is why this row. But y dash to y, it gives a small angle cos theta. And not y dash to y, yeah, right. Then z dash to y, you see, it is on the other quadrant. And therefore, you extend this y-axis in the negative direction. Then you will find that this angle is 90 minus theta. The projection of z dash on the y-axis will be then sine theta. Of course, there is in the negative direction, that is, there is a negative here, so negative sine theta. And in the similar way, you can write this also. So we have got a transformation matrix, which a vector represented in the new frame, x, y dash, z dash, can be transformed to the old frame, x, y, z, by this particular matrix. So this is a coordinate transformation matrix. And we here what is involved is only the rotation about one particular axis. And we will go to the next one, is also the old slide. The similar way, the argument is similar. This is very elementary. Just check, we will check this also, and then the next one we will take for assumed. Next, I am trying to rotate about the y-axis, because y-axis I am calling another symbol called psi. So now I have the vector in the new frame, that is my x dash, y doesn't undergo any change, whereas z becomes z dash, x becomes x dash. So my new frame is x dash y z, my old frame is x y z, and a vector in the new frame is vx dash vy vz. And let us see how vx dash can contribute to x. So x dash to x, there is a small angle psi, so cos theta. And vy does not have any component along x because they are orthogonal, so that's why 0. And vy dash is what is the angle to x? This angle is 90 minus theta, so cosine of that is sine theta. So that is sine psi here, theta, sorry, psi, sine psi. And the next one is Vy does not, here, because the rotation is about the y-axis. The second component here is the y-axis component will depend only on y. That's why it is 0, 1, 0. And the other one is also fairly simple. The same explanation, what I have told, we just, these PowerPoints will be, this lecture and things will be available to you. You should check this. This is very simple. And see what we considered. We considered an x-axis rotation by theta, a y-axis rotation psi, and a z-axis rotation pi. And we got in each case, you remember, I have always written C new to old, means a vector in new frame to a conversion to the old frame. That's what I have written everywhere, new to old. New to old. So these things are very important. It has to be meticulously followed. Now, this figure was given, but then a slightly different way. Now, what have we done? Now, let's say there, the previous examples, we have taken an orthogonal frame and one rotation about each at a time we consider. Now, we are now going to consider, take x, y, z, first give theta rotation about x. So, I have got y dash and z dash. This y and z no more exists, but in our computation it will exist. But in the pictorial sense for our visualization, to make it simple, only all these things are shown. So this rotation has resulted z to z dash and y to y dash, x remains the same. The same scenario, the second rotation, if I take about this new y, the new y is called y dash, and angle psi rotation about the new y-axis, which is y dash, that will change z dash to some other angle, some other position, and that I am calling it z double dash. And x also it will change. The x change is called x dash here. And the rotation it has gone is by psi angle. And now this is about the new y-axis I am calling y dash axis. Earlier in our individual examples, we called x, y, z. Now x, y dash, and now the third angle, I have a resultant z double dash. The z double dash I am taking. This is the resultant z axis, which is the new z axis is 2 times it has undergone change, therefore 2 dashes here. And now this resultant z axis, I give a rotation, a pi angle, which makes x dash to a new position x double dash and y dash to a new position y double dash. So what I have got is x double dash, y double dash, z double dash. That is my new frame. By doing a sequence of rotations in this fashion, which I have explained, by theta about x and psi about the new y, resultant y, and pi about the resultant z, I have attained a frame x double dash, y double dash, and z double dash. And this frame, if I call my body frame, user body frame, and the original frame, if I call the navigation frame, maybe it could be inertial, then there will be a relationship between this frame to this frame. What is that relation? That is quite interesting. That is, what is the transformation matrix from x double dash, y double dash, z double dash to x, y, z after going through 3 sequential rotations the way we have explained here. Okay? Yeah? Now, and that will be, see, the final thing is here. You see, there is a rotation about, it's a dash axis, is Z double dash axis by pi angle. And that corresponding to that, there is a transformation, and that is the rightmost one. And then just wait. There is a, yeah. You look at this form, cos minus sine, and this one. It is same as what we have initially discussed. It's same as the form is the same. And this one, cos sine, you just look at this one. It's same as this particular flow. Look at the first one, cos minus sine, sine cos. It is same as this one. So, and that is why we were spending this simple experiments or way of explaining to reach to slowly getting into real complexities. So now this sequential rotation, the transformation matrix between this x, y, z to x double dash, y double dash, z double dash is given by the product of these three matrices. When the last class, please note this and this I have interchanged. There was an error. Please note that. So this is one problem that when sometimes anybody can mix up things. I have mixed up last time. Middle one, whatever way to do it doesn't change. So these two were interchanged in the last presentation. Please note that was an error. And the product of this will give you the new frame, that is a body frame, new frame, body frame, to the old frame, the starting frame, end frame. The net result I am talking. So when you multiply this three matrices, they are going, you will get a lot of sine into cos into so many things will come. I'll show you one particular case. Now suppose, so let us put it like this because it looks very elegant. So we call A, B, C and all that for elegance. It is C stands for the coordinate transformation matrix from body frame to navigation frame. Now, suppose we want to get the other way, navigation frame to body frame, reverse. If you want to get that, simply take the transpose of this. That's what I have done here. Because these are all orthogonal matrices. What is orthogonal matrices? We take any two column, the dot product column vectors, the dot product will be 0. Check here, 1 into 0 is 0, 0 into this cos is 0, this into this is 0, you add up all of them, you will get 0. And you take this and this, you take 0 into 0 is 0. This is minus sine into cos plus sine into cos, that will cancel, you will get 0. Again the dot product is 0. You take this to this, this to this, or any row matrix, two row vectors you see, this to this you see, this to this you see, you will get the dot product will be 0. So this is an orthogonal matrix. This is an orthogonal matrix. This is an orthogonal matrix. When you take the product of all the three, still it will be an orthogonal matrix, and that this is also an orthogonal matrix. I hope you have understood what is orthogonality. Now I will call the name orthonormal. It's not only orthogonal, its magnitude is unity. That is what we call is normal. Orthonormal. You take the magnitude of each column 1, cos square plus sine square 1, sine square plus cos square 1. You take this way, any row you take the magnitude is 1, cos square plus sine square 1, sine square plus cos square 1. So like that you can check all this, the magnitude is 1. And if you take the product matrix is also a 3 by 3 matrix. And there also whatever orthogonality we have been mentioning here, they will be orthogonal. each column, each row, and their magnitudes will be unity and so on. And therefore, this matrix is a orthonormal matrix. And for an orthonormal matrix, actually you want an inverse of this to get n to be. For an orthonormal matrix, the inverse is nothing but transpose. So therefore, we simply take the transpose of this. If you have three matrices A into B into C, the transpose by you would have studied already. It is A transpose, B transpose, C transpose. This I hope you should be recalling your mathematics, what you have studied from matrix algebra. This A transpose I am calling C1, B transpose I am calling C2, C transpose I am calling C3 for some other purpose. And these transposes are written here. So later we will be using it. Now, one question can come. Why you are using a sequence of angles? Is it an elegant way? Is it a useful way? There is a block here. There are some problems I have written, which are not intentionally, I have not explained. Now, why there is a problem with this kind of representation of transformation matrix? And is it useful? Is it not there any better method to to represent a coordinate transformation? In fact, there is a better method which we will be studying later. But then the question can come, then why should we study this one? If it is a better method, why don't we directly go to that better method? Why should we study unnecessarily this and waste time? It is not so because of the following reason. Now, you see there is an instrument here. There is this particular machine. The whole thing has got, see this arrow I have written, the first axis. The whole thing can rotate about this particular axis. And here in this direction, second axis, these are called gimbals. This Y module, entire Y module is hinged on to this particular axis. It can rotate 360 degrees about this particular axis, this one. Then you see there is a black one seen here. I have a third axis marked here. And the black one can rotate about this particular axis, all the 360 degrees. And this is a machine. It's called Angular Motion Simulator. We simply call it AMS. And suppose I have, aligned this. I pulled it down and make this axis normal to these two axes. That is the starting point. And then I will drive the outer, the middle, the inner. That's what we call the outer gimbal, the middle gimbal, and the inner gimbal. By giving angular rotations to these three is equivalent to saying that theta is the outermost, psi is the middle, pi is the innermost. So, in a practical system, suppose I want to test a package which consists of gyroscopes. In the ground, suppose I want to test by giving angular rates about its three axes. I have only one mechanism, and that is this angular motion mechanism, angular motion simulator. There is no other way of testing it in the ground to give simultaneous angular motion about all three axes, x, y, z, of the body axis. Cannot be given by any other method. And it can only be implemented by this kind of a gimbal arrangement. In which case, what happens? The outermost is rotated this axis is changing, this axis is also changing. That's what is really happening when this is rotated. This axis is changing, this axis is also changing. And the middle gimbal is rotated and it changes the relative angle between the outer and the inner. And that is what and here is happening. And if you rotate the middle one also, the relative angle between all the three will change except that particular axis. And that is what is happening here. So this particular mechanization is called, the name Euler angles, a way of representing coordinate transformation matrix. And that's what it is useful for. This why we need to study Euler angles to representation, why it becomes important, because of this particular reason. And what is the problem? The problem is, suppose I put this white middle gimbal little bit more up, what will happen? The inner axis, this is the inner axis, innermost axis, third axis, will get aligned with the outermost axis. Can you imagine? You rotate it a little bit up, and this inner axis will go and get aligned with this. That means when the middle gimbal moves by 90 degrees, two axes coincide, and 1 degree of angular motion is lost. And this is what is written here, the middle angle problem, the middle gimbal problem, losing 1 degree of freedom. In mathematical way, we will be showing later. Today time will not be there, but we will be addressing to that in that way. So this why I have shown this picture is that the significance of Euler, even though there are better methods to represent coordinate transformation matrix, the Euler angle methodology cannot be thrown out, because for testing any physical system in the ground to give angular rates about the three axes, this is the only way it can be done. That demands the use of Euler angles, which we have just discussed. Where are we with respect to the time? Can you give the feedback? Should we enter into the next one? The 50 minutes is up, means we will go for question and answer. Can you give the feedback? Jinju? Jinju? Hello? Jinju? Jinju, unmute your mic. Can I just start 2 minutes and then stop here? I think this is the boundary for question answer. Okay. I take 2 minutes. Kind of a homework also I will give.
Okay.
See,
Okay.
This is just I'm introducing, and this we will take in the next class, but just introducing. This will be, you please take it as a homework. Time derivative of the direction cosine matrix. This direction cosine matrix we have explained in very simple terms. And angular rotations, earlier we called theta, psi, pi. Here, because I am taking some delta, theta x, delta, theta y, delta, theta z, it's a different name, that's all. And these are the same as the previous one. We have to use that. How to find out, suppose I do this, want to find out the time derivative of the direction cosine matrix. What do I do? So that's what it's about. This is a very important step. Next, immediately. And that's what I think we will stop here and take questions. And there is a 50 minutes is over. Jinju, is it okay? Jinju, you can unmute your mic.
Any questions from the participants?
Any question? Feedback also can be there, See, we want to improve our presentation, and it should be useful. See, today I have purposely went very slow so that whatever we learn, it should get accumulated and we should get some result out of it. Otherwise, in the class means we can, from the looking at each student, we get a feedback. Eye feedback is there. So here that is not there. That is the only problem, even though this has got other advantages. So you should please ask questions. Even if you don't understand, please tell me. Then only we can improve this. Okay. Please don't go at this point of time. All of them I request especially to be continue to be present and then tell your comments whether the speed of presentation is over, whether you are able to understand. Otherwise, I will call out. I think that only is possible. I think. Abhijit JJ. Abhijit JJ. Abhirag. Abhirag.
Hello, President sir.
Yes, Abhirag, എന്തെങ്കിലും പറയൂ.
സാർ വെബിനാറൊക്കെയുള്ളായിരുന്നു സാർ.
മനസ്സിലായിരുന്നോ?
സാർ ഈസി ആയിട്ട് മനസ്സിലായി സാർ.
വെരി ഗുഡ്. അഖിൽ അൺമ്യൂട്ട്, ഫോൺ അൺമ്യൂട്ട് ചെയ്തിട്ട് പറ.
ഹലോ സാർ.
അഖിൽ പറ, മനസ്സിലായോ?
മനസ്സിലായി സാർ. ഇവിടെ കുറച്ച് നെറ്റ്വർക്ക് പ്രോബ്ലം ഉണ്ട്, ഇടയ്ക്ക് കേൾക്കാൻ പറ്റില്ല.
മനസ്സിലായോ? കേട്ടത് എത്രയും മനസ്സിലായോ?
മനസ്സിലായി സാർ.
ഓക്കെ. പിന്നെ അഭിജിത്ത് ഫോൺ അൺമ്യൂട്ട് ചെയ്തിട്ട് റിപ്ലൈ ചെയ്യേ. അഭിജിത്ത്. അബ്ദുൽ റഹീം ഫോൺ അൺമ്യൂട്ട് ചെയ്തിട്ട് ആൻസർ ചെയ്യേ. അബ്ദുൽ റഹീം. അബ്ദുൽ, മനസ്സിലായിരുന്നോ?
കുഴപ്പമില്ലായിരുന്നു, മനസ്സിലായിരുന്നു. ഇടയ്ക്ക് നെറ്റ്വർക്ക് പ്രോബ്ലം ഉണ്ടായിരുന്നു.
നെറ്റ്വർക്ക് പ്രോബ്ലം അല്ലാതെ എല്ലാം മനസ്സിലായോ?
തുടക്കത്തിൽ മനസ്സിലായി.
ഓക്കെ. ബാക്കിയുള്ളത് കേട്ടില്ല.
ഇല്ല സർ.
അപ്പൊ ഈ മെറ്റീരിയല്, ഈ വീഡിയോ അവൈലബിൾ ടു യു, അത് കേട്ടിട്ട് അടുത്ത ക്ലാസ്സിൽ സംശയം ചോദിക്കാം കേട്ടോ.
ഓക്കെ സർ.
ഓക്കെ. അഖിൽ പറഞ്ഞു. Amina is our current S8 S7 student, or S8 student.
Hello sir.
Hello Amina, yeah, or final year student, right Amina? Amina പറയൂ, മനസ്സിലായോ Amina?
Sir, നെറ്റ് കണക്ഷൻ പ്രോബ്ലം ഉണ്ടായിരുന്നു, കുഴപ്പമില്ല.
നെറ്റ് കണക്ഷൻ പ്രോബ്ലം അല്ല, ബാക്കി കേട്ടത് എന്തെങ്കിലും മനസ്സിലായോ?
സർ.
അഞ്ജിത ഫോൺ അൺമ്യൂട്ട് ചെയ്തിട്ട് പറയൂ. ആരോമൽ.
ആരോമൽ
പറയൂ. ആരോമൽ, ഫീഡ്ബാക്ക് പറ.
ക്ലാസ് കൊള്ളാം, എനിക്ക് ഇഷ്ടപ്പെട്ടു. സ്പീഡ് കറക്റ്റ്, സ്ലോ തന്നെ എനിക്ക് മനസ്സിലാവുന്നുണ്ട്.
ഞാൻ സ്ലോ ആയിട്ട് തന്നെ
താങ്ക് യു.
കാരണം പലതരത്തിലുള്ള
താങ്ക്
ആൾക്കാരുണ്ടല്ലോ,
യു.
മനസ്സിലാവണമല്ലോ.
അതെ സാർ.
അതെ, സോ അല്ലാതെ നമ്മള് ഓക്കെ, സോ ദാറ്റ് ഈസ് വൈ സ്ലോ ആയിട്ട് പോകുന്നതിന്റെ പർപ്പസ് ആയിട്ട് തന്നെ സ്ലോ ആയിട്ട് പോകുന്നത്. ഓക്കെ ഓക്കെ, താങ്ക് യു.
കഴിഞ്ഞ ക്ലാസ്സിന്റെ കാര്യങ്ങൾ ഓർമ്മിച്ചു തരുന്നു.
ഓക്കെ, വെരി ഗുഡ്. ആശിഷ്
താങ്ക് യു.
മാത്യു, Ashish Matthew, unmute your mic and give your feedback. Ashish Matthew. Okay, he is not responding. Devika Thambi, unmute your mic and respond. Mic on ആക്കിയിട്ട് പറയൂ ദേവിക.
ഹലോ സാർ.
പറയൂ ദേവിക.
സാർ, ഇടയ്ക്ക് കുറച്ച് നെറ്റ് ഇഷ്യൂ ഉണ്ടായിരുന്നു, ബാക്കിയൊക്കെ കേൾക്കായിരുന്നു.
ഓക്കെ, അപ്പൊ ഈ വീഡിയോ കേൾക്കണം. വീഡിയോ കേട്ടിട്ട് അടുത്ത ക്ലാസ്സിൽ സംശയം ഉണ്ടെങ്കിൽ പറയണം. ദേവകൃഷ്ണ
സർ.
പറയൂ ദേവ.
സാർ, ഞാൻ സ്റ്റാർട്ടിങ് കുറച്ചില്ലായിരുന്നു, പക്ഷെ ബാക്കി വന്നതിന് ശേഷം മനസ്സിലായിരുന്നു.
വെരി ഗുഡ്. ഗുഹൻ.
Sir, yes, sir.
Could you make
Yes, sir.
sense out of today's lecture?
Yes, sir. I could able to do that. Only
Okay.
one doubt, sir.
Yeah,
If
please ask.
if the accelerometer is fixed in the body frame, then
Yeah.
how we can measure the acceleration, because the force cannot be measured if the frame is not inertial. Intense law is valid only in the inertial frame of reference. So if the
Yeah.
body,
No,
if the
I'll answer you. This last class did you attend?
is a but half only I was able to attend the last class. Today
Is
only
it?
I attended the whole
Okay,
class.
okay. Very good question. Yeah, let us try to answer that. You see, the accelerometer, I'm drawing in a very crude way. This figure I had drawn last time in one of the slides. And I have a necked pendulum, finely necked, very small hinge. And I call this as a crude pendulum. I have some technique. All those things are not shown here. So that I keep it in this position normally, let us say. Now, if there is an acceleration coming here, the pendulum will move down, right? Do you accept this?
Yes, sir. Due to inertia,
Yeah.
it will be, yes, sir.
Yeah, whether your body is moving, accelerating, rotating, and all those things, fine.
Yes.
But this will always happen.
Yes, sir.
And this is the only thing that will happen. So we sense this deflection. There are mechanisms, pick-off coils, very sensitive pick-off coils, which will sense this deflection.
Yes, sir.
And that convert into, that deflection is calibrated into how much of acceleration has come. And that is only the inertial acceleration. Now, what do I mean by this? Suppose I take this accelerometer to a 100-floor tall building and assume we are in vacuum and
Okay.
freely falling. This fellow is freely falling without rotating, just down.
Yes, sir.
Then what happens is the gravitation acts on each molecule of the case and each molecule of the pendulum and the hinge and this mounting, etc. Everywhere it is equal. There is no differential force, and therefore this pendulum will not deflect at all, even though the entire thing is being acted upon by the gravitation vector, which makes it to accelerate down. Okay?
Okay.
Therefore, it cannot measure the gravitation acceleration. No, cannot measure. It can only measure inertial acceleration, and that the meaning of that inertial acceleration in our day-to-day life, when we are sitting in the bus seat, when the driver is accelerating the bus in the forward direction, you get pressed backward. That is inertia force. And this
Yes,
is
sir.
exactly that, nothing else. The lift example you would have studied, it is exactly that. And this is also called measurable inertial force. Because gravitation is also an inertial force, because this cannot be measured, I will call it measurable inertia force. And there's a specific name for this, it's called specific force or specific acceleration, which is measured by the accelerometer here. Okay? So your question was, our vehicle is accelerating, it is not in inertial frame, how can it measure? By being there in an accelerating thing, the accelerometer itself is the observer who is accelerating. Okay, and that is a reason, fundamental reason why it cannot measure gravitation. Okay, and
Okay, sir.
this inertia force, that is the only one it can measure. But we need both this inertia force as well as gravitation for our navigation computation. And this one we need to take out from a mathematical model. And this one we can measure using the accelerometer, vectorially add up the two and whatever. This is what I was telling the other day. So did your question is answered?
Yes, sir. This answers. Thank you, sir.
Thank you. So who else is left? Who else is left? Hello? Guhan, you are from IAST? You are from which? Your affiliation? You are from LMCST? Hello? Whom I talked just now? Hello? Please come back. Come on. ആരാ എന്റെ പേര് ജിഞ്ചു ആ പുള്ളിയുടെ പേരെന്തായിരുന്നു
ആരാ സർ
സംസാരിച്ച പയ്യൻ
സർ IST എന്നുള്ളതാണ്
IAS എന്നുള്ള പയ്യനാണോ പോയോ
ഗുഗൻ സർ ഗുഗൻ സർ ഗുഗൻ
ഗുഗൻ യാ
Left eye, sir, left eye.
ഗുഗൻ ആണ്
ഓക്കെ
ലെഫ്റ്റ് ആയി
ഓക്കെ ബാക്കി ഹരിശങ്കർ കമാൺ
സർ
മനസ്സിലായിരുന്നോ
സർ ക്ലിയർ ആയിരുന്നു
ഇന്നിപ്പോ ഞാൻ ഗുഹനുമായിട്ട് എക്സ്പ്ലെയിൻ ചെയ്തത് നമ്മൾ ഇനി ഒരിക്കൽ കൂടെ പല പ്രാവശ്യം വരും ഗുഹൻ പിന്നെ കുറച്ച് അഡ്വാൻസ്ഡ് ആയിട്ട് ചോദിച്ചുകൊണ്ട് അങ്ങനെ പറഞ്ഞതേ ഉള്ളൂ ചോദിക്കുമ്പോൾ ഉത്തരം പറയണമല്ലോ ഓക്കെ നമ്മളത് പതുക്കെ അതിലേക്ക് വരും കേട്ടോ ഓക്കെ ജെബിൻ
മനസ്സിലായി ജിജോ
രാജ് Jijo L. Raj. Yeah. He is not responding. Sajida Surya. What is this? Ratnendra Singh. Yeah. Hello, Mr. Ratnendra Singh.
Yes, sir.
Sir, you are from IAST?
Yes, sir. I am from IST.
Yeah. So, what is your feedback, sir?
So, actually, these lectures are very informative. Our faculty has told us to attend these lectures. It's good, sir. So, I am able to understand the coordinate transformation and all.
Yeah. So, we will go slowly because otherwise, what I find is speeding up. We have all the second year students also here. So, all of them it should cater to. That's why the speed has been reduced. So I hope as long as please continuously attend to get benefited, because we will be going to so many other things as time goes on, including quaternion mechanization, so many things. Okay, thank you. So here somebody there, webinar, that is our students. Okay, overall now I hand over to Jinju and team.
Vipin? Hello, Vipin is there?
Hello, Miss. Hello. Hello.
Yeah. Vipin,
Yes.
Vipin Paran, teacher vilikkunnallo.
Vipin,
Oh,
you can conclude the session.
okay. Good evening, all. On behalf of EC Department, I, Vibinam K of S4EC, take this opportunity to propose vote of thanks. First of all, I extend my most sincere thanks to the Almighty God for making today's session a grand success. I would like to express my gratitude to our principal, Dr. P.P. Mohanlal, for his excellent presentation and making this session interesting and meaningful. Thank you, sir. I would like to thank our HOD, Professor Surya SR, and staff coordinator, Professor Jinju Joy, and Professor Sajida for their moral support and guidance. Thank you, my dear teachers. I also extend my thanks to my friend Josmon SS of S4EC for his enormous cooperation for this webinar. Thank you, Josmon. Last but not the least, I would like to thank all the participants in this webinar. Once again, thank you all.
Okay, so we'll wind up, and let me also thank all of you. My special request is those who are attending, please continue to attend, because then only there is any use. Otherwise, simply like, one starting webinar lecture, an overview, and after that everything will be forgotten. So my aim is at the end of the year, we should come out with a very good knowledge about a particular field, which is very, very important. Thank you.